Okay, everyone, we're about to begin our very last lesson for this unit, applications using logarithms. So we're going to get a lot of the word problems we got earlier on in this unit, except now we have the power to solve for exponents as well. All right, and we don't need to use graphing technology to do it. We can do it using logarithms. Okay, so our learning goals then are to solve exponential equations using the laws of logarithms, extend my knowledge of solving exponential and logarithmic equations to real-world situations, and reflect on the reasonableness of your answer always. Okay, so everything we do is going to be word problems here. Okay, so we'll see a lot of the applications that exist in the real world with respect to exponential functions. So to start, if you did want to receive a deeper history of logarithms, this link here from Britannica will go through a lot more detail than what I provided in terms of the history and exactly how it was developed and what happened and all that information. So if you wanted to look at that, you can certainly do so. Okay, but I am going to go ahead and begin our lesson. Now, recall that our exponential functions that we deal with that are going to be part of these real-world applications are going to be of the following form. Okay, so they'll be of the form of, we can use y or f at x equals a times b to the x, or y equals a times b to the x. Okay, but remember that the a value, it represents the y-intercept, or when it comes to a word problem, we call it the initial value, so the starting amount. Okay? Initial value. All right. And a version of the form to solve real-world problems, we also discussed already, would be of the following. So using, instead of b, using y equals a, and then 1 plus what's known as the growth rate, gr, to the power of x. So b for growth, for exponential growth, is equal to 1 plus the growth rate. The growth rate will always be given in a word problem. So if something's growing by 20% or whatever it might be, the growth rate will be given to you. For decay, b is going to equal 1 minus decay rate. Again, the decay rate should be given to you. So all you need to know is that this is the formula we are going to be working with, the two formulas that we're going to be working with today. Now, as a quick refresher, let's remember a lot of these questions, if we're ever solving for x, the exponent, we're going to convert into logarithms. So remember that logarithms are of the following form, where the exponent is equal to the log of a with a base b. Okay? Then to actually use our calculator, we can't use our calculator with any base. The base has to be 10. Okay? And so there's a way to convert this into being base 10, and that is with x equals take the log of your a value with a base 10, divide it by the log of your b value with a base 10. That will allow us to plug into our calculator there. And we'll be doing this basically for every question we do when we're asked to solve exponents. So get used to this format here and converting an exponential format into logarithmic to solve for x. Okay? All right. So let's just quickly go over growth rate and decay rate. Okay, so say we have a function v at t equals 20 times 1.02 to the power of t. My first question to you, is it growth or decay? And how can you tell? Well, the answer is that it is growth. And here's how you can tell. Anything above 1 So anything greater than 1 will be growth, okay? Anything greater than 1. Whereas below here, if you have a b value, if your b value is greater than 1, okay, then that means you did 1 plus something, 1 plus a growth rate. In this case, we'll get to what that growth rate was. But if you have decay, your b value should be less than 1. Okay, and in that case, it's 0.65. So this is, in fact, decay. Okay, what is our initial value for each of these? Very easy. It's your a value, which is 20. And in this case, it is 1,000. What is the actual growth and decay rate? Well, to figure that out, all you really need to do is find the difference between, in this case, in our first situation, our difference between 1 and 0.02. Well, it obviously grew by 0.02. So that's the common sense way of doing it. Your growth rate is 0.02, which is 2%, right? Converted as a percentage is a growth rate of 2%, multiplied by 100, okay? Algebraically, to find that, all you do is you go b equals 1 plus growth rate. Well, if you know that b is 1.02, you can find the growth rate by subtracting 1 on this side. Right? So 0.02 is your growth rate. Okay, it's that simple. Now, to find your decay rate, just do 1 minus 0.65 in our case here. So there's your 0.65. Do 1 minus 0.65. Okay, and so your decay rate is 0.35. Okay. Or in terms of percentage, 35%, right? Multiplied by 100. Okay. So let's begin, now that we kind of understand the concept of growth and decay and how to get information from that, let's actually start a word problem. Okay? So a new car costs $35,000. It loses 22% of its value each year after it is purchased. Write an equation to represent the value of the car. Okay, so we must do here an equation. It's losing 22%. So would you say that it's decay or growth if it's losing 22%? I think it's safe to say that that's a decay question. So grab your decay formula, which is in its simplest form, y equals a times 1 minus the decay rate to the power of x. Okay? Now, I want to use variables that makes more sense here. So I'm dealing with the value of a car after each year, which is time. Okay, so value, my two variables are value, okay, of the car in dollars and time in years. So instead of just y, because I'm doing a word problem here, I'm gonna use the letters v and t. So when I write the equation, I'm gonna have v at t equals a times 1 minus dr to the power of t. Okay, so it's no longer x. We're now using a t. Okay, let's plug in our values if we're losing 22%. So v at t equals my initial, so my a value, my initial is 35,000. Okay, so 35,000 times 1 minus my decay rate is 22%. As a decimal, however, that is written as 0.22. So 1 minus 0.22 to the power of t. Finish it off by cleaning up the 1 minus 0.22, okay, which is 0.78 to the power of t. There is your final equation. Okay, so v at t equals 35,000 times 0.78 to the power of t. Okay, so let's take a look at what we're being asked here. So determine the value of the car after 30 months. Okay, but my time, because the value goes down each year, that's something needs to be fixed here, because we need to know after 30 months, but we're in years, right? We're in years. So how many years is 30 months? Simply do 30 months. Okay. 2 years is 24 months. Sorry about that. Do it divided by 1 year. So 12 months. Okay. And so what do you get? 2.5 years, which makes sense. 2 years is 24 months. 30 months would be 2.5 years. So our t then is going to be 2.5. I need to substitute 2.5 into my equation and then figure out what the value will be at that point. So let's do that. V, and remember the function notation, V at 2.5 is equal to 35,000 times 0.78 to the power of 2.5. Now remember, this 2.5 here is just there for communication purposes. Okay, nothing, there's no multiplication there. I know that's a common mistake. So all you're doing is punching this into your calculator. Make sure you do exponents before multiplying by 35,000. So do 0.78 to the power of 2.5, hit equals, then times it by 35,000. You get 18,806.35 cents. There's your value of the car, approximately after 2.5 years. Okay, next. How long will it take for the car to be worth 5,000? So now we're being asked how long it will take, and we're given the value. We're actually given V at t as 5,000. We're given the value. We need to actually solve for t, time. How long will it take? How many years? So let's write out the equation. Let's see what happens. I'm going to replace V at t with 5,000. So replace the whole thing with 5,000. Now, I know that to solve for an exponent, I need to use logarithms, right? However, right now this isn't in the proper format that I want it in. I want it in this format. Or, sorry, I'll use the letter A. So how do we get in this format? Right now there's this 35,000 that's in the way of it being in this format. Well, we can move the 35,000 over to the other side. Okay, all you do is divide it out on both sides because it's times. Divide it out on both sides. Okay, it'll cross off on the right, so I'm not going to write it. And then just plug that into your calculator. 5,000 divided by 35,000. And do quite a few decimal places. Okay, I would do at least 5 decimal places just to get a more accurate answer. Okay. Now, to actually solve this, we have to go to logarithmic. Okay, we don't know how to solve this any other way. We have to go to logarithmic form. So remember that logarithmic form looks like this. X equals log of A to base B. Well, my base is 0.78. That's B. This is A. All right, so T, in my case, it's not X. It's T equals log of 0.142857 with a base of 0.78. Now, this is not with bases of 10, and to use our calculator, we've got to switch it to bases of 10. So we've got to do what I showed here. Oops. Right there, right? So let's go. T then equals the log base 10 of 0.14287 divided by the log of 0.78, the base of 10. And there you have it. We are going to get 7.8 years, okay, or approximately 8 years. That makes sense, right? That makes sense. If it's decaying exponentially, it makes sense that it would take about that long. If up here, 2.5 years brought it down to 18,000, after 7.8 years, it'll be down to 5,000. Okay, so again, check the reasonableness of your answer. Moving on. All right, the population of a town had 2,500 residents in 2005 and grew, okay, keyword, at a rate of 3.5%. Okay, 3.5% just as a decimal will be 0.035 because I need to use decimals in my equation. Write an equation to represent the population of the town after t years. Okay, so here's let's use variables that make sense. Population, t years. So t is obviously going to be my time. So I have t. I'll use the letter capital P to represent population. So I'll have P at t is equal to, this is my initial, it's my A. Okay, and actually I will write out the general form just so we have it here. It's a growth rate question. So you have your A, which is your initial value, in our case is 2,500, then bracket 1 plus my growth rate of 0.035 as a decimal, and then to the power of t instead of x. Let's clean this up. Becomes P at t is equal to 2,500 times 1.035 to the power of t. Okay. Determine the population of the town in 2016. Well, if the initial population was in 2005, to find how many years, so we're being asked to sub in the amount of years. You do not sub in 2016. You sub in, because the time started in 2005. You have to sub in 2016 minus 2005 to find the difference. You sub in 11 years. Okay? So let's go ahead and do that. Let's find P at 11 is equal to 2,500 times 1.035 to the power of 11. Okay? So pull out your calculator there. Make sure you do your exponent before you multiply by 2,500. You get 3,650 people. Right? That's the population. Keep going. It says, when will the population double? Okay. So that, again, it's asking when. It's asking us to solve for t. Right? When will it happen? After how many years? And the population initially, if the initial A value was 2,500, what's the doubled population that we are concerned with? Okay? Doubled, of course, would be 5,000. So that's our doubled population. So that is going to be our P at T is going to be 5,000 people. All right. So P at T, I'm just writing out the equation to start. Okay, and now replace P at T, so replace it with 5,000. All these questions are going to follow the same pattern until we get to something new that we'll do below. But so this is in the form we want. We need to divide out this 2,500 first, right? Divide it out on both sides. So that it cancels on this side. And we're left with 2, right? 5,000 divided by 2500 is 2 equals 1.035 to the power of t. Not the way we want it. We want to change this to logarithmic. So we want it to be in this format here, and I'm not going to write it out again, the general form, it's right here. Okay, right there. So the log of a to base b. So log, here's our a, here's our b, log of 2 to base b of 1.035. Okay, sorry, you can barely see that. Now convert it to base 10 so we could plug it into our calculator. Okay, so base 10 up here. So take the log of a with base 10 divided by the log of b with base 10. And what do you get as your time when you plug in log 2 on your calculator divided by log 1.035? You get 20.15. So it'll take just over 20 years, so that's in years, for the population to double and get to 5,000. Okay? All right, 2 more problems that I want to try, and I need to introduce to you a concept called doubling time and half-life. All right, so doubling time and half-life. And all that is, the equations are going to change slightly. All right, there's going to be a slight change, but these equations here deal a lot with your pharmaceutical medicine, for example, like I mentioned in previous lessons, your Advils, any sort of medicine has what's called a half-life, meaning that it decreases to half its potency after a certain amount of hours or days that it's been sitting. Okay, that's all that means. Doubling time means that after a certain amount of time, a population or something, an investment or something, will double. And so the equations are a little bit special. They look a little bit different. They're going to look like this. All right. So I'm going to use the letters. It doesn't matter what letters you use. F at t is equal to an initial value a times 2. It's always going to be this. So it's no longer 1 plus the growth rate for doubling time. It's times 2 because it's doubling. That's the rate. It's doubling. To the power of, and this is where it gets a little bit different, okay, it's going to be t over d. Where? Okay, so let's make note. A is the initial. T is time. It'll almost always be time there. D is your doubling time. And this will always be given to you, okay? Your doubling time will always be given to you. So this is a special version of the formula. Now the letters are interchangeable, except for D and A. We typically use those letters, A as the initial, D as what's called the doubling time. It's the same thing for half-life, except instead of 2, guess what your decay rate will be? If you guessed 0.5 or half, you got it right. T over, and now instead of D for doubling time, we're going to use H for half-life. Okay, so make note of that. Okay, so these are just special equations. All right, whenever you see the words half-life or doubling time, you're going to use those special equations. Okay, so let's start a question. A 200-gram sample of a radioactive substance has a half-life of 138 days. Okay, so that's our H. Half-life. Determine the mass that remains after 5 years. My T is 5 years. It's asking for my mass. So instead of using the letter capital F, I'm going to use the letter capital M. I want to find my mass after 5 years. So let's write out the equation using proper letters. Okay, so using mass. So at 5 years, all we need to do is sub in 5 for t, okay, and then make sure we plug in our h and our a values. By the way, what is our a value? 200 grams was our initial. Okay, 200 times 0.5 to the power of t, which we know is 5 years. Okay, so we have a problem here. T is 5 years, but our half-life is 138 days. Those have to line up. Those have to match up with each other. Okay, they can't have years and days. They both either have to say years or they both have to say days. What's the easiest way to do this? Should we convert days to years or years to days? Let's convert years to days. We have 5 times 365 days in a year for 5 years. So what is your value there? 1825. That's how many days 5 years is. So time is 1825 divided by a half-life of 138. So on your calculator, you're going to do 0.5 to the power of brackets 1825 divided by 138, close bracket, hit your equal sign, and times by 200. Okay? And I suppose you can even just divide the 18, we can do another step and just divide 1825 divided by 138, but you can do it all in one step if you follow what I just outlined. So look what happens to this radioactive material. It started as 200 grams, and because it halves its life every 138 days, after 5 years, okay, after 5 years, it's going to be down to almost nothing, just 0.02 grams. Okay, so if you had some sort of medicine that expired and 5 years later you tried to take it, it could be that it has no potency whatsoever anymore, okay, depending on what its half-life is. Final example. A certain type of bacteria given a favorable growth medium doubles in population every 6.5 hours. Okay, so doubling time. So my D is equal to 6.5 hours. Given that there is approximately 100 bacteria to start with, so my A is 100, how long will it take to grow to 300? How long will it take? So we're solving for T. To grow to 300. Okay, so we need to assign a letter. So this is a population of bacteria. So I'm going to use the letter P. Okay, so the population with respect to time is equal to 300. Okay? So do you understand how I'm using the letter P? It's a population of a bacteria. So I'm using the letter P there. So P at T is equal to 300. Let's write out the equation. It's doubling time, so it's a 2 T over D. Sub in all your numbers. As you can see, we don't know what T is. We need to solve for T. Okay? So, in order to do so, we got to clean this up a little bit. We can solve for that exponent, the numerator, but first we need to get rid of that 100 like we did in the previous questions. Divide it out. You're left with 3 equals 2 to the power of t over 6.5. Okay, so we can solve for this whole exponent, the whole thing, okay, t over 6.5. If we convert it, remember, x is equal to the log of a to base b, except in our case, our x is a fraction, t over 6.5. So t divided by 6.5 is equal to, instead of x, we have t divided by 6.5 is equal to the log, this is our a, this is our b. Okay? Now converted to base 10, t over 6.5 is equal to log of 3 with a base 10 divided by log of 2 with a base 10. What is t over 6.5 equal to? Once I do this in my calculator, log of 3 divided by log of 2, it is equal to 1.59. I'm not done yet though, right? I need to solve for t. I'm close. I'm so close. Well, what if I was to assume that this is really over 1, and so I have a fraction with an unknown equal to another fraction? Okay? To solve this, simply cross multiply. So t times 1 is equal to 1.59 times 6.5. So t is equal to 10.33 hours. So the bacteria will get to a population of 300 after 10 hours. Okay? That concludes this lesson and concludes the unit. So please practice this, practice converting exponential equations into logarithmic equations and then converting them to base 10 so you can punch them into your calculator. That's it.